Part 1. Before the solar system, the cosmic origins, long before the sun ever shone, before the planets spun in their orbits, and before the solar system, as we know it existed, there was a profound emptiness, a vast, cold, and nearly infinite expanse of interstellar space. This void was not truly empty, though it stretched for light years in every direction, filled only with the faintest whispers of matter and energy. In this primordial darkness, the universe was a tapestry of subtle forces and ancient remnants, the legacy of cosmic events that had unfolded over billions of years. Yet, even in this apparent nothingness, there were seeds of creation. Drifting silently through the spiral arms of our young Milky Way galaxy was a giant molecular cloud, a colossal, diffuse aggregation of gas and dust, spanning dozens, sometimes hundreds, of light years. These clouds are the cradles of stars and planets, the nurseries where the next generation of cosmic objects would be born. The particular cloud that would one day give rise to our solar system was immense, its mass measured in thousands of times that of our sun, and its temperature just a few degrees above absolute zero. The composition of this cloud was a direct inheritance from the universe's earliest moments. The vast majority of its mass was hydrogen, the simplest and most abundant element, forged in the first minutes after the Big Bang. Helium, the second most common element, was also present, a relic of primordial nucleosynthesis. But this cloud was not composed solely of these light elements. Scattered throughout its expanse were traces of heavier elements: carbon, oxygen, nitrogen, iron, silicon, and more. These atoms had been created in the hearts of ancient stars through the process of stellar nucleosynthesis, and then cast into the galaxy by the explosive deaths of those stars, supernova, that had torn themselves apart, enriching the interstellar medium with the building blocks of planets, life, and everything we know. These heavier elements, though making up only a tiny fraction of the cloud's total mass, were of profound importance. They existed as tiny grains of dust, microscopic flecks of silicates, carbon compounds, and metals, each one a relic of a star's final moments. Over millions of years, these grains drifted through the cloud, colliding, sticking together, and sometimes breaking apart. They absorbed and emitted faint glimmers of starlight, cooling the cloud and allowing it to collapse more easily under its own gravity. This cosmic dust was the raw material from which planets, moons, asteroids, and comets would eventually form. Every rock on Earth, every drop of water, every atom in our bodies, each can trace its origin to these ancient grains, forged in the hearts of stars long dead. The calm before creation, a delicate balance. For millions upon millions of years, the giant molecular cloud existed in a state of delicate equilibrium. The inward pull of gravity, acting on every atom and dust grain, was balanced by the outward pressure of the gas, heated by the faint glow of distant stars and the occasional shock wave from a supernova. The cloud was cold, dark, and stable, its internal motions slow and ponderous. In some regions, turbulence stirred the gas, creating denser knots and filaments, while in others, the cloud was almost perfectly still. This balance could not last forever. The universe is a place of constant change, and even the most stable structures are eventually disrupted. The trigger for the collapse of our solar system's parent cloud is still debated by astronomers. Some suggest that a nearby supernova exploded, sending a shock wave racing through the cloud, compressing it and tipping it over the edge. Others proposed that the gravitational influence of a passing star, or the slow, inexorable density waves of the Milky Way's spiral arms, provided the necessary nudge. Perhaps it was a combination of these factors, or something else entirely. What is certain is that around 4.6 billion years ago, the balance was broken. Collapse and the birth of a star, a region of the cloud, perhaps several light years across, began to collapse under its own gravity. As it did, the material within it was drawn ever closer together, increasing in density and temperature. The collapse was not uniform. Some parts of the cloud fell inward faster than others, creating clumps and filaments that would eventually become stars and planetary systems. The process was governed by the fundamental laws of physics, gravity, thermodynamics, and the conservation of angular momentum. As the cloud contracted, its initial, almost imperceptible rotation began to speed up. This is a consequence of the conservation of angular momentum. As the radius of a spinning object decreases, its rotation rate increases just as a figure skater spins faster when pulling in their arms. The collapsing cloud flattened into a vast, rotating disk, hundreds of astronomical units across. At the center of this disk, the material became so dense and hot that nuclear fusion was ignited. A new star, our sun, was born, shining for the first time in the darkness. But the story of the solar system's birth was only just beginning. The disk of gas and dust surrounding the newborn sun, the solar nebula, was a place of intense activity, where the raw materials of planets, moons, and smaller bodies were being assembled. The next chapters would see the gradual, chaotic, and often violent process by which the familiar worlds of our solar system took shape. Part 2. The trigger and the collapse, the solar nebula, takes shape. The collapse of the giant molecular cloud was not a sudden, explosive event, but rather a gradual, relentless process that unfolded over hundreds of thousands, even millions, of years. As gravity drew the gas and dust inward, the region destined to become our solar system began to change in profound ways. The once diffuse and tranquil cloud became a dynamic, turbulent environment, its fate sealed by the inexorable pull of its own mass. The catalyst, a cosmic nudge. The precise cause of the collapse remains a subject of scientific investigation, but the leading theories all point to some form of external disturbance. Perhaps a massive star nearing the end of its life exploded in a supernova, sending a shock wave barreling through the interstellar medium. This shock wave, traveling at thousands of kilometers per second, would have compressed the gas in its path, creating pockets of higher density. Alternatively, the gravitational influence of a passing star, or the slow passage of the cloud through one of the Milky Way's spiral arms, could have provided the necessary push. Whatever the catalyst, it was enough to tip the balance, setting in motion a chain of events that would ultimately lead to the birth of a star and its attendant planets. Fragmentation and collapse. The birth of protostars. As the cloud collapsed, it did not do so uniformly. Instead, it fragmented into smaller clumps, each destined to become a star or a system of stars. Within the region that would become our solar system, the density increased dramatically. The temperature, too, began to rise, as the energy of infalling material was converted into heat. The collapse was governed by the interplay of gravity, pressure, and rotation, each shaping the outcome in subtle but important ways. The conservation of angular momentum played a crucial role. As the cloud contracted, its rotation rate increased, causing it to flatten into a disk. This disk, known as the protoplanetary disk or solar nebula, was the birthplace of the planets, moons, asteroids, and comets. The vast majority of the material, over 99%, was drawn toward the center, where it formed a dense, hot core. Here, the pressure and temperature soared to extraordinary levels, eventually reaching the threshold for nuclear fusion. Ignition, the birth of the sun. At the heart of the collapsing cloud, the temperature climbed to millions of degrees. The hydrogen atoms, squeezed ever closer together, began to fuse, forming helium and releasing vast amounts of energy in the process. This was the moment of ignition, the birth of a new star. Our sun, a G-type main sequence star, began to shine, its light and heat flooding the surrounding disk. The energy released by fusion created an outward pressure that balanced the inward pull of gravity, stabilizing the young star and halting its further collapse. The sun's birth was a transformative event. Its intense radiation and powerful solar wind began to shape the environment of the protoplanetary disk, driving away the remaining gas and setting the stage for the next phase of planetary formation. The protoplanetary disk, a cosmic workshop surrounding the newborn sun, was a vast, spinning disk of gas and dust, stretching for hundreds of astronomical units. This disk was not uniform. Its temperature and composition varied dramatically with distance from the sun. Close to the star, the heat was intense, and only materials with high melting points, metals and rocky silicates, could remain solid. Farther out, beyond the so-called frost line or snow line, temperatures were low, enough for volatile compounds like water, ammonia, and methane to condense into ices. Within this disk, countless processes were at work. Tiny grains of dust, composed of silicates, carbon, and metals, collided and stuck together, forming larger and larger aggregates. These aggregates, initially held together by electrostatic forces, grew into pebbles, then rocks, then boulders. As they increased in size, gravity began to play a more significant role, pulling them together into even larger bodies. The formation of planetesimals, building blocks of planets. As the boulders grew to sizes of a kilometer or more, they became known as planetesimals, the first true building blocks of planets. Gravity now dominated their interactions, causing them to attract and collide with one another. This stage, known as runaway accretion, saw the largest planetesimals grow ever faster, sweeping up smaller bodies in their path and clearing out their orbits. The process was chaotic and violent. Collisions were frequent, and not all were gentle mergers. Many were catastrophic impacts that shattered bodies and sent debris flying. Over time, however, a few large planetesimals emerged as the dominant players, their gravity allowing them to gather more and more material. These would become the planetary embryos, the seeds of the planets themselves. The solar nebula evolves, a system in transition. As the sun continued to shine and the disk evolved, the remaining gas was gradually blown away by the solar wind and radiation pressure. The era of planet formation was drawing to a close, but the story was far from over. The planetary embryos, now numbering in the dozens, continued to collide and merge, their orbits shifting and interacting in a complex gravitational dance. Some of these embryos would go on to become the terrestrial planets: Mercury, Venus, Earth, and Mars, while others would be ejected from the system or incorporated into the growing gas giants. The leftover debris, unable to coalesce into planets, would become the asteroids and comets, relics of a bygone era. The solar system as we know it was beginning to take shape, a dynamic, evolving system born from the ashes of ancient stars and the relentless forces of gravity and physics. Part 3. The protoplanetary disk, chaos, chemistry, and the birth of worlds. The protoplanetary disk that encircled the young sun was a place of extraordinary complexity and ceaseless activity. To the naked eye, it would have appeared as a vast, flattened cloud, glowing faintly in the light of the newborn star. But within this disk, on scales ranging from microscopic dust grains to kilometer-sized boulders, the processes that would ultimately give rise to planets, moons, and smaller bodies were already underway. The structure and dynamics of the disk. The disk itself was not a uniform structure. Its density, temperature, and composition varied dramatically with distance from the sun, closest to the star. Within what astronomers call the hot inner disk, temperatures soared to thousands of degrees Kelvin. Here, only the most refractory materials, those with the highest melting points, could survive in solid form. These included metals like iron and nickel, and silicate minerals such as olivine and pyroxene. Any ices or volatile compounds would have been vaporized by the intense heat, existing only as gas. Farther from the sun, beyond the so-called frost line or snow line, the temperature dropped precipitously. Here, water vapor could condense into solid ice, along with other volatiles like ammonia and methane. This region, the cold outer disk, contained a much greater abundance of solid material, since ices are far more common in the universe than metals or silicates. The location of the frost line was crucial. It marked the boundary between the rocky, terrestrial planets and the gas and ice giants that would form farther out. The disk was also in constant motion. Gas and dust orbited the sun in nearly circular paths, but small differences in velocity, turbulence, and pressure gradients created a dynamic environment. Shocks and waves rippled through the disk, driven by gravitational instabilities, magnetic fields, and the influence of the growing sun. These processes helped to concentrate material in certain regions, creating the seeds for planet formation. The chemistry of the solar nebula. The chemical composition of the disk was inherited from the interstellar cloud that birthed it, but the conditions within the disk allowed for a rich and varied chemistry. In the hot inner regions, high temperatures drove the formation of minerals and metals, while in the cooler outer regions, ices and organic molecules could form and survive. One of the most important processes was the condensation sequence, the order in which different materials solidified out of the gas as the disk cooled. The first solids to form were tiny grains of refractory minerals, known as calcium aluminum-rich inclusions, CaEs. These are among the oldest objects in the solar system, dating back over 4.56 billion years, and are found today in primitive meteorites called chondrites. Following the formation of CaEs, other minerals and metals condensed, followed by silicates and, farther out, ices. Organic molecules, including simple hydrocarbons and amino acids, could also form in the cold outer disk, either through chemical reactions on the surfaces of dust grains or by irradiation from cosmic rays and ultraviolet light. These organics would later be incorporated into comets and asteroids. and eventually delivered to the young Earth, providing the raw materials for life. Dust coagulation, from grains to pebbles. The first step in planet formation was the growth of dust grains into larger aggregates. In the microgravity environment of the disk, tiny particles of silicate, metal, and ice collided and stuck together, held by electrostatic forces, much like the way static electricity causes dust to cling to surfaces on Earth. These fluffy aggregates, often just a few microns across, gradually grew larger as they swept up more material. This process, known as dust coagulation, was remarkably efficient. Within a few thousand years, many grains had grown to millimeter or even centimeter sizes, forming what are known as pebbles. These pebbles, in turn, collided and stuck together, forming larger and larger clumps. The structure of these aggregates was often highly porous, resembling a loose pile of dust rather than a solid rock. However, as the aggregates grew, new challenges emerged. Collisions at higher speeds could cause the clumps to bounce off each other or even fragment, halting growth. This bouncing barrier and fragmentation barrier are still active areas of research in planetary science. Some regions of the disk may have overcome these barriers through local concentrations of dust, turbulence, or the presence of sticky ices, allowing growth to continue. The meter-size barrier and the leap to planetesimals, as pebbles grew into rocks and boulders, reaching sizes of a meter or more, they encountered another obstacle, the meter-size barrier. At this scale, the drag from the surrounding gas caused these bodies to spiral inward toward the sun on timescales of just a few hundred years, a process known as radial drift. If nothing intervened, much of the solid material in the disk would be lost to the sun before it could form planets. Yet somehow some bodies managed to leap past this barrier and grow into kilometer-sized planetesimals. Several mechanisms have been proposed to explain this rapid growth. One leading theory is the streaming instability, a process in which local concentrations of pebbles and rocks interact with the gas in the disk, creating dense filaments that collapse under their own gravity to form planetesimals directly. This process can occur rapidly, allowing the formation of large numbers of planetesimals in a relatively short time. Planetesimal formation. The first building blocks of planets. Once planetesimals formed, gravity became the dominant force. These kilometer-sized bodies could attract and accrete smaller objects, growing ever larger in a process known as runaway accretion. The largest planetesimals grew fastest, sweeping up material in their orbital paths and clearing out gaps in the disk. The population of planetesimals was diverse. Some were rich in metal and rock, forming in the hot inner disk, while others, forming farther out, contained significant amounts of ice and organic material. Collisions between planetesimals were frequent and often violent, leading to fragmentation, melting, and differentiation, the separation of materials by density, with heavier metals sinking to form cores and lighter silicates forming mantles and crusts. Some planetesimals grew large enough to become planetary embryos, bodies hundreds or thousands of kilometers across. These embryos would go on to become the cores of planets, or, in some cases, be ejected from the system or destroyed in giant impacts. The role of radioactive heating and differentiation. An important factor in the evolution of planetesimals was the presence of short-lived radioactive isotopes, such as aluminum-26 and iron-60. These isotopes, produced in supernova and incorporated into the solar nebula, released heat as they decayed. In planetesimals large enough to retain this heat, the interior could become warm enough to melt, allowing differentiation to occur. This process created bodies with metallic cores and silicate mantles, the precursors to the structure of the terrestrial planets. The heat from radioactive decay also drove volcanic activity and the release of gases, creating thin atmospheres around some planetesimals. In the outer solar system, where ices were abundant, this process could lead to the formation of subsurface oceans, as seen today on moons like Europa and Enceladus. The early solar system, a violent and dynamic place. The environment of the early solar system was anything but peaceful. The disk was filled with planetesimals and embryos, their orbits crossing and intersecting in a chaotic dance. Collisions were frequent, ranging from gentle mergers to catastrophic impacts that shattered bodies and sent debris flying across the system. Some of this debris would be swept up by growing planets, while the rest would remain as asteroids, comets, and meteoroids. The scars of this violent era are still visible today in the heavily cratered surfaces of the Moon, Mercury, and other ancient worlds. The formation of the giant planets, farther from the Sun, beyond the frost line, the abundance of ices allowed planetesimals to grow much larger, forming massive cores that could quickly accrete thick envelopes of hydrogen and helium from the surrounding disk. This process gave rise to the gas giants Jupiter and Saturn and the ice giants Uranus and Neptune. The formation of these giant planets had profound effects on the rest of the solar system, their immense gravity shaping the orbits of smaller bodies and triggering migrations that would reshape the architecture of the system. The dissipation of the disk and the end of planet formation. As the Sun matured, its intense radiation and solar wind gradually blew away the remaining gas in the disk, halting the growth of the giant planets and leaving behind a system of planets, moons, asteroids, and comets. The era of planet formation was over, but the story of the solar system was just beginning. The next chapters would see the final assembly of the planets, the bombardment of their surfaces by leftover debris, and the emergence of the conditions that would one day allow life to flourish on Earth. Part 4. The final assembly collisions, chaos, and the late heavy bombardment. As the protoplanetary disk thinned and the Sun's radiation swept away the last vestiges of gas, the solar system entered a new and tumultuous phase. The era of planetesimal and planetary embryo formation gave way to a period of intense dynamism and violence, a cosmic crucible in which the final architecture of the solar system would be forged. The planetary embryos, titans in a crowded arena. By this stage, the inner solar system was populated by dozens of planetary embryos' bodies, ranging from hundreds to thousands of kilometers in diameter. These embryos, along with countless smaller planetesimals, orbited the Sun in a crowded, ever-shifting ballet. Their orbits were not perfectly circular or neatly spaced. Instead, gravitational interactions constantly perturbed their paths, leading to frequent close encounters and collisions. The process of planetary assembly in this environment was governed by a principle known as oligarchic growth. The largest embryos, or oligarchs, dominated their local regions, sweeping up smaller bodies and growing ever larger. However, as their masses increased, so did their gravitational influence, stirring up the orbits of neighboring embryos and planetesimals. This led to a cascade of collisions, some gentle, resulting in mergers, and others catastrophic, shattering bodies and creating vast clouds of debris. Giant impacts. The sculptors of worlds. The most dramatic events of this era were the giant impacts collisions between planetary embryos that could reshape entire worlds. These titanic encounters released energies equivalent to billions of nuclear bombs, melting and vaporizing rock, and in some cases, stripping away entire crusts or atmospheres. One of the most famous of these events is the hypothesized Theia impact. According to the leading theory, a Mars-sized body, dubbed Theia, collided with the proto-Earth in a glancing blow. The impact was so immense that it ejected a vast amount of material into orbit around Earth, which eventually coalesced to form the Moon. This event not only created our unique satellite, but also profoundly affected Earth's rotation, tilt, and internal structure. Other giant impacts may have played similar roles in shaping the planets. Mercury's unusually large iron core, for example, may be the result of a colossal collision that stripped away much of its original mantle and crust. Venus's slow retrograde rotation could also be the legacy of a massive impact or series of impacts. The clearing of the inner solar system. As the number of planetary embryos dwindled through mergers and ejections, the inner solar system gradually settled into a more stable configuration. 4 major terrestrial planets, Mercury, Venus, Earth, and Mars, emerged from the chaos, each occupying a distinct orbit. The leftover debris, unable to coalesce into another planet due to the gravitational influence of Jupiter, became the asteroid belt, a region populated by countless rocky and metallic bodies, ranging from tiny pebbles to the dwarf planet Ceres. But the violence was not yet over. The newly formed planets continued to be bombarded by the remaining planetesimals and debris, their surfaces scarred by countless impacts. This period, known as the Late Heavy Bombardment, would leave an indelible mark on the history of the solar system. The Late Heavy Bombardment, a cataclysmic epoch, roughly 4.1 to 3.8 billion years ago, the solar system experienced a dramatic spike in impact, rates a period known as the Late Heavy Bombardment, LHB. Evidence for this cataclysm comes from the cratered surfaces of the Moon, Mercury, and other ancient bodies, as well as from isotopic dating of lunar rocks brought back by the Apollo missions. The cause of the LHB is still debated, but the leading explanation is the Nice model named after the city in France, where it was developed. According to this model, the giant planets Jupiter, Saturn, Uranus, and Neptune underwent a period of orbital migration. As Jupiter and Saturn crossed a 2-to-1 orbital resonance, their gravitational interactions destabilized the orbits of Uranus and Neptune, causing them to scatter outward into the Kuiper belt. This migration sent a gravitational shock wave through the solar system, destabilizing the orbits of countless planetesimals and small bodies. Many were flung inward, bombarding the terrestrial planets, while others were ejected into interstellar space or sent into the distant Oort cloud. The LHB was a time of extraordinary violence, with impacts large enough to vaporize oceans, melt crusts, and alter atmospheres. Consequences of the bombardment, seeds of life and destruction. The Late Heavy Bombardment was both a threat and an opportunity for the young Earth and its neighbors. On the one hand, the impacts were devastating, capable of sterilizing the surface and delaying the emergence of life. On the other hand, they may have delivered vital ingredients, water, organic molecules, and other volatiles essential for the development of life. Many scientists believe that much of Earth's water was delivered by carbonaceous chondrite asteroids and comets during and after the LHB. These bodies, rich in ices and organics, could have seeded the early oceans and provided the raw materials for prebiotic chemistry. The same processes may have occurred on Mars and other worlds, raising the tantalizing possibility that life could have arisen elsewhere in the solar system. The end of the bombardment and the dawn of stability. As the supply of impactors dwindled and the planets settled into their final orbits, the solar system entered a new era of relative calm. The surfaces of the terrestrial planets, once molten and cratered, began to cool and solidify. Atmospheres formed and evolved, shaped by volcanic outgassing, impacts, and the influence of the sun. On Earth, the conditions were finally right for life to take hold. The first oceans formed, the crust stabilized, and the earliest forms of life, simple, single-celled organisms, emerged. The scars of the solar system's violent youth remained, etched into the surfaces of the moon. Mercury and other ancient bodies, silent witnesses to a time when worlds were forged in fire and chaos. The legacy of the early solar system, the events of this formative era, set the stage for everything that followed. The architecture of the planets, the composition of their atmospheres, the presence of water and organics, all were determined by the processes of accretion, collision, and migration that played out in the first few 100 million years. The solar system we inhabit today is the product of this long and tumultuous history, a dynamic and ever-changing system shaped by the interplay of cosmic forces. Part 5. The Sun, Anatomy, Evolution, and the Engine of the Solar System. The Sun is not merely the central star of our solar system. It is the gravitational anchor, the primary source of energy, and the ultimate architect of planetary environments. Understanding the Sun's formation, structure, and ongoing activity is essential to grasping the evolution and current state of every world that orbits it. The birth of the Sun, from protostar to main sequence. The Sun's story began in the heart of the collapsing molecular cloud, where gravity compressed gas and dust into an ever-denser core. As the core's temperature and pressure soared, it entered the protostar phase, a luminous contracting sphere shrouded in the remnants of the solar nebula. During this time, the protosun was surrounded by a thick envelope of infalling material, accreting mass from the disk and radiating energy primarily in the infrared. Eventually, the core temperature reached about 10 million Kelvin, hot enough for nuclear fusion to ignite. Hydrogen nuclei protons began to fuse into helium via the proton-proton chain reaction, releasing vast amounts of energy in the form of gamma rays and neutrinos. This energy created an outward pressure that balanced the inward pull of gravity, halting further collapse. The Sun had reached hydrostatic equilibrium and officially entered the main sequence, a stable phase that would last for billions of years. Stellar classification and the Sun's place among the stars. Our Sun is classified as a G2V star, a G-type main sequence star. It is a yellow dwarf with a mass of about 1.989 times 10 kilograms, 333,000 times that of Earth, and a radius of about 696,340 kilometers. Its surface temperature is approximately 5,778 Kelvin, giving it a characteristic yellow-white glow. While the Sun is often described as an average star, it is actually more massive and luminous than about 90% of stars in the Milky Way, most of which are red dwarfs. Its stability and longevity have been crucial for the development of life on Earth, providing a consistent energy source over geological timescales. The Sun's internal structure, layers of fire and plasma. The Sun's interior is a complex, multi-layered structure, each region governed by distinct physical processes. The core, extending from the center to about 25% of the solar radius. The core is the Sun's powerhouse. Here, temperatures reach 15 million Kelvin, and pressures are over 250 billion times Earth's atmospheric pressure. Nuclear fusion occurs almost exclusively in this region, converting about 600 million tons of hydrogen into helium every second and releasing energy that will eventually escape as sunlight. The radiative zone. Surrounding the core, this region extends from about 0.25 to 0.7 solar radii. In the radiative zone, energy is transported outward by the absorption and re-emission of photons, a process known as radiative diffusion. Photons take a random walk, being absorbed and re-emitted countless times, so that it can take over 100,000 years for energy produced in the core to reach the next layer, the tachocline. This thin, transitional layer between the radiative and convective zones is believed to be the seat of the Sun's magnetic dynamo. Here, the differential rotation of the Sun's interior and outer layers generates powerful magnetic fields. The convective zone. From about 0.7 solar radii to the visible surface, the temperature drops enough for heavier ions to retain electrons, making the plasma more opaque. Energy is now transported by convection. Hot plasma rises toward the surface, cools, and sinks back down in massive churning currents. This process creates the granular pattern seen on the Sun's surface. The photosphere. The surface of the Sun, about 500 kilometers thick, is where the plasma becomes transparent enough for photons to escape into space. The photosphere is what we see as sunlight, and it displays a mottled granular appearance due to convection cells. The chromosphere and transition region. Above the photosphere lies the chromosphere, a reddish layer visible during solar eclipses. The transition region is a thin, irregular layer where temperatures rise rapidly from about 20,000 Kelvin to over 1,000,000 Kelvin. The corona. The Sun's outer atmosphere, the corona, extends millions of kilometers into space. Despite its low density, the corona is incredibly hot over 1,000,000 Kelvin due to magnetic heating mechanisms that are still not fully understood. The corona is the source of the solar wind and is visible as a pearly halo during total solar eclipses. Solar magnetism. The dynamo at work. The Sun's magnetic field is generated by the movement of electrically conducting plasma in its interior, a process known as the solar dynamo. The differential rotation of the Sun, faster at the equator than at the poles, and the convective motions in the outer layers twist and tangle magnetic field lines, leading to a rich variety of magnetic phenomena. Sunspots. These are temporary, cooler regions on the photosphere appearing dark by contrast. Sunspots are areas where Intense magnetic fields inhibit convection, reducing the heat flow from below. They often occur in pairs or groups with opposite magnetic polarity. Asterisk the solar cycle. The number of sunspots waxes and wanes in a roughly 11-year cycle, known as the solar cycle. At solar maximum, the sun is dotted with sunspots, and solar activity, such as flares and coronal mass ejections, increases. At solar minimum, sunspots are rare, and the sun is relatively quiet. The full magnetic cycle, including a reversal of the sun's global magnetic field, lasts about 22 years. Asterisk solar flares and coronal mass ejections, CMEs, when magnetic field lines become twisted and reconnect, they can release enormous amounts of energy in the form of solar flares, bursts of radiation across the electromagnetic spectrum. CMEs are even more dramatic, hurling billions of tons of plasma into space at speeds of up to 3,000 kilometers per second. If directed toward Earth, CMEs can trigger geomagnetic storms, disrupt satellites and power grids, and create spectacular auroras. The solar wind and the heliosphere. The sun's corona is so hot that its gravity cannot contain it, resulting in a continuous outflow of charged particles, the solar wind. This wind blows outward in all directions, creating a vast bubble in the interstellar medium known as the heliosphere. The boundary where the solar wind slows to subsonic speeds is called the termination shock. Beyond this lies the heliopause, where the pressure of the solar wind and the interstellar medium are in balance. The solar wind shapes the environments of all the planets, drives the formation of planetary magnetospheres and auroras, and protects the solar system from some of the cosmic rays that pervade interstellar space. The Voyager 1 and 2 spacecraft have crossed the heliopause, entering interstellar space while still feeling the distant influence of the sun. The sun's influence on planetary evolution. The sun's energy and magnetic activity have profound effects on the atmospheres, climates, and potential habitability of the planets. Its ultraviolet radiation can strip away atmospheres as seen on Mars and Mercury, while its warmth allows liquid water to exist on Earth. The solar wind interacts with planetary magnetic fields, creating auroras and shaping magnetospheres. Over billions of years, the sun's luminosity has gradually increased, altering the climates of the planets. In the distant future, as the sun evolves into a red giant, it will dramatically reshape the solar system, engulfing the inner planets and shedding its outer layers as a planetary nebula. The sun as a laboratory for physics. The sun is not only the engine of the solar system, but also a natural laboratory for studying fundamental physics. Observations of solar neutrinos have provided crucial tests of nuclear fusion theories and the properties of neutrinos themselves. The study of solar oscillations, helioseismology, has revealed details of the sun's internal structure and dynamics that cannot be observed directly. A star among billions. While the sun is unique to us, it is one of hundreds of billions of stars in the Milky Way, each with its own story of formation, evolution, and planetary companions. By studying the sun, we gain insight not only into our own origins, but also into the processes that shape stars and planetary systems throughout the universe. Part 6. The Inner Solar System Worlds of Rock, Metal, and Diverse Destinies. The inner solar system, lying within the frost line of the protoplanetary disk, is home to the terrestrial planets, Mercury, Venus, Earth, and Mars. These worlds are united by their rocky compositions and relatively small sizes, but each has followed a dramatically different evolutionary path, shaped by their distance from the Sun, their initial endowments of volatiles, and the violence of their early histories. Mercury, the iron planet. Mercury, the closest planet to the Sun, is a world of extremes and enigmas. With a diameter of just 4,880 kilometers, it is the smallest of the major planets, yet it possesses a disproportionately large iron core, making up about 85% of its radius. This gives Mercury the highest density of any planet in the solar system, aside from Earth. Mercury's surface is ancient and heavily cratered, resembling the highlands of the Moon. The largest impact feature is the Caloris Basin, a colossal crater over 1,500 kilometers in diameter, formed by an impact so powerful that it created weird terrain on the planet's opposite side. The surface is also marked by long, sinuous cliffs called lobate scarps, evidence of the planet's slow contraction as its core cooled. The origin of Mercury's massive core remains a subject of debate. One hypothesis suggests that a giant impact early in its history stripped away much of its original mantle and crust, leaving behind a metal-rich remnant. Another theory posits that intense solar radiation vaporized and blew away the lighter silicate materials, or that Mercury formed from metal-rich material in the innermost part of the solar nebula. Mercury's rotation is locked in a 3-to-2 resonance with its orbit. It rotates 3 times on its axis for every 2 orbits around the Sun. This results in a single solar day, sunrise to sunrise, lasting 176 Earth days. With virtually no atmosphere to retain heat, surface temperatures swing from 430 degrees Celsius, 800 degrees Fahrenheit, on the day side to minus 180 degrees Celsius, minus 290 degrees Fahrenheit on the night side. Despite its proximity to the Sun, Mercury harbors water ice and organic compounds in permanently shadowed craters at its poles, as revealed by the Messenger spacecraft. These deposits are thought to have been delivered by comets and volatile-rich asteroids, demonstrating the complex interplay of processes that have shaped even the innermost planet. Venus, the runaway greenhouse. Venus, often called Earth's sister planet due to its similar size and mass, is a cautionary tale of planetary climate gone awry. Venus likely began with conditions not unlike Earth's, possibly including oceans of liquid water. However, its slightly closer proximity to the Sun set it on a radically different path. As the young Sun brightened, Venus's surface warmed, causing any oceans to evaporate. Water vapor, a potent greenhouse gas, trapped more heat, accelerating the warming and a runaway feedback loop. Eventually, the surface became hot enough to bake carbon dioxide out of the rocks, further thickening the atmosphere. Today, Venus's atmosphere is 96.5% CO, with a surface pressure 92 times that of Earth and temperatures hot enough to melt lead, about 465 degrees Celsius or 870 degrees Fahrenheit. The surface of Venus is shrouded in thick clouds of sulfuric acid, making direct observation impossible in visible light. Radar mapping by spacecraft like Magellan has revealed a landscape dominated by vast volcanic plains, highland regions called tesserae, and enormous shield volcanoes, such as Ma'at Mong's. unique features called coronae large. Circular structures formed by upwelling mantle plumes dot the surface. Venus shows evidence of global resurfacing events, where massive volcanic activity may have repaved the planet, erasing most of its older craters. Its slow retrograde rotation, spinning backwards compared to most planets, and 243 Earth day length remain mysterious, possibly the result of tidal interactions with its dense atmosphere or a giant impact. Despite its hellish conditions, Venus is a laboratory for understanding planetary atmospheres, greenhouse effects, and the delicate balance that makes a world habitable. Earth, the living planet. Earth is unique in the solar system, not only for its abundant liquid water and oxygen-rich atmosphere, but also for its dynamic geology and thriving biosphere. Its history is a story of constant change, shaped by internal and external forces. Asterisk plate tectonics. Earth's crust is divided into rigid plates that float atop the semi-fluid mantle. Plate tectonics recycles carbon, regulates the climate, and drives the formation of mountains, ocean basins, and continents. This process is unique among the terrestrial planets and is critical for long-term climate stability. Asterisk the magnetic field. Generated by the motion of molten iron in the outer core, the geodynamo, Earth's magnetic field shields the planet from the solar wind, preventing atmospheric erosion and protecting life from harmful radiation. Asterisk atmosphere and hydrosphere. Earth's atmosphere is a delicate balance of nitrogen, oxygen, and trace gases maintained by biological and geological processes. The presence of liquid water, likely delivered by asteroids and comets during the late heavy bombardment, is essential for life and climate regulation. Asterisk the moon. Earth's large natural satellite stabilizes the planet's axial tilt, moderating seasonal variations and possibly aiding the development of complex life. The moon itself is thought to have formed from the debris of a giant impact, and its gravitational pull creates tides that influence oceanic and biological cycles. Asterisk life. Earth is the only known planet to host life, from simple microbes to complex multicellular organisms. Life has profoundly altered the planet's atmosphere, surface, and even its geology, creating a feedback loop that has sustained habitability for billions of years. Mars, the divided world. Mars, the fourth planet from the Sun, is a world of stark contrasts and tantalizing mysteries. Its southern hemisphere is dominated by ancient, heavily cratered highlands, while the northern hemisphere is a lower benefier, smoother plain, and enigmatic hemispheric dichotomy that may be the result of a colossal impact. Mars's history is intimately tied to water. Orbital imagery and rover missions have revealed dried-up river valleys, lake beds, and deltas, as well as minerals that form only in the presence of liquid water. About 3.5 billion years ago, Mars had a thicker atmosphere and a warmer climate, allowing water to flow on its surface. However, Mars's small size doomed it to a different fate than Earth. Its interior cooled rapidly, shutting down its magnetic dynamo and leaving the atmosphere vulnerable to erosion by the solar wind. As the atmosphere thinned, surface temperatures plummeted, and most of the water either escaped to space or became locked in polar ice caps and subsurface reservoirs. Despite its cold, dry present, Mars remains geologically active. It boasts the largest volcano in the solar system, Olympus Mons, and the vast canyon system Valles Marineris. Recent evidence suggests that briny liquid water may still exist beneath the surface, and recurring slope linear dark streaks that appear seasonally hint at ongoing processes. Mars is a prime target in the search for past or present life, and its exploration continues to yield new insights into planetary evolution, climate, and the potential for habitability beyond Earth. The inner solar system, a laboratory of planetary science. The terrestrial planets are a testament to the diversity of outcomes possible from similar starting conditions. Their differences are the result of subtle variations in mass, composition, distance from the Sun, and the timing and nature of catastrophic events. By studying these worlds, we gain not only a deeper understanding of our own planet, but also a window into the processes that shape rocky planets throughout the galaxy. Part 7. The asteroid belt relics of the solar system's formation. Between the orbits of Mars and Jupiter lies the asteroid belt, a vast region populated by millions of rocky and metallic bodies. Contrary to popular imagination, the asteroid belt is not a densely packed field of tumbling rocks, but rather a region where the objects are separated by vast distances on average, hundreds of thousands of kilometers apart. Yet, the belt is a treasure trove of information about the early solar system, origins and composition. The asteroid belt is not the shattered remains of a destroyed planet, but rather a planet that never formed. During the early stages of the solar system, Jupiter's immense gravity stirred up the material in this region, preventing it from accreting into a single large body. Instead, the belt became a repository for leftover planetesimals' primitive building blocks that never coalesced into a planet. Asteroids are classified by their composition, which reflects the conditions in the solar nebula at their formation. C type, carbonaceous asteroids, the most common, making up over 75% of known asteroids. These are dark, rich in carbon, and contain water-bearing minerals and organic compounds. They are found mostly in the outer belt and are considered the most primitive, unaltered material from the solar system's birth. S-type silicaceous asteroids, brighter and composed mainly of silicate rocks and metals like iron and nickel. These are more common in the inner belt and are thought to have undergone some thermal processing. M-type metallic asteroids. Found in the middle belt, these are composed primarily of metallic iron and nickel. They may be the exposed cores of differentiated protoplanets that were shattered by collisions. Ceres and the Dawn mission. The largest object in the asteroid belt is Ceres, a dwarf planet about 940 kilometers in diameter. Ceres is unique. It is large enough for its gravity to have shaped it into a nearly spherical body, and it shows evidence of differentiation, a rocky core, and an icy mantle. The Dawn spacecraft, which orbited Ceres from 2015 to 2018, revealed a world with mysterious bright spots in a crater composed of sodium carbonate salts left behind by briny water erupting from the interior. Ceres also has a cryovolcano, Ahuna Mongs, and may harbor a subsurface ocean, making it a potential target in the search for extraterrestrial life. Asteroid families and collisions. The asteroid belt is not static. Collisions between asteroids are common on geological timescales, creating families of fragments that share similar orbits and compositions. These collisions can produce meteoroid small fragments that sometimes fall to Earth as meteorites, providing direct samples of early solar system material. Some asteroids, known as near-Earth objects, NEOs, have orbits that bring them close to Earth. These bodies are monitored closely, as impacts with large NEOs have played a significant role in Earth's history, including the extinction of the dinosaurs 66 million years ago. The asteroid belt is a time capsule. The belt preserves a record of the conditions and processes that prevailed during the solar system's formation. By studying asteroids and meteorites, scientists have learned about the composition of the solar nebula, the timing of planetesimal formation, and the delivery of water and organics to the early Earth. Part 8. The outer solar system, the gas giants, and their moons. Beyond the asteroid belt lie the gas giants Jupiter and Saturn, and the ice giants Uranus and Neptune. These worlds are fundamentally different from the terrestrial planets, both in composition and in the complexity of their systems. The formation and migration of the giant planets. The gas and ice giants formed beyond the frost line, where ices were abundant and allowed the rapid growth of massive cores. Once these cores reached a critical mass, about 10 Earth masses, they accreted thick envelopes of hydrogen and helium from the solar nebula. The migration of these planets, driven by interactions with the disk and each other, reshaped the architecture of the solar system, scattering smaller bodies and influencing the formation of the Kuiper belt and Oort cloud. Part 9. The ice giants Uranus and Neptune. Uranus and Neptune, the outermost major planets, are distinct from Jupiter and Saturn in both composition and appearance. Uranus, the tilted world. Uranus is unique for its extreme axial tilt, about 98 degrees, causing it to rotate on its side relative to its orbit. This tilt is likely the result of a collision with a large protoplanet early in its history. Uranus's atmosphere is rich in hydrogen, helium, and methane, the latter giving it a blue-green color by absorbing red light. Asterisk rings and moons. Uranus has a faint system of dark rings and at least 27 known moons, including Miranda, which displays bizarre patchwork terrain indicative of past geological upheavals. Asterisk interior. The planet's interior is thought to be a slushy mixture of water, ammonia, and methane ices surrounding a rocky core. Its magnetic field is both offset from the center and tilted relative to the rotation axis, creating complex magnetospheric dynamics. Neptune, the windy giant. Neptune, the most distant planet, is a dynamic world with the fastest winds in the solar system, over 2,000 kilometers per hour. Like Uranus, its blue color is due to atmospheric methane. Asterisk atmosphere and weather. Neptune's atmosphere is marked by large dark storms, such as the Great Dark Spot observed by Voyager 2 in 1989. The planet radiates more heat than it receives from the sun, driving its active weather systems. Asterisk Triton. Neptune's largest moon, Triton, is a captured Kuiper belt object with a retrograde orbit. Triton is geologically active, with nitrogen geysers and a thin atmosphere. Tidal forces are slowly drawing Triton inward, and it may eventually be torn apart to form a new ring system. Part 10. The trans-Neptunian region. The Kuiper belt and Oort cloud. Beyond Neptune lies a vast, mysterious realm populated by icy bodies, dwarf planets, and comets, the Kuiper belt and the Oort cloud. The Kuiper belt, The Kuiper belt extends from about 30 to 55 astronomical units from the Sun and contains thousands of icy objects, including Pluto, Haumea, Makemake, and Eris. These bodies are remnants of the early solar system, preserved in the deep freeze of the outer reaches. Asterisk Pluto. Once considered the ninth planet, Pluto is now classified as a dwarf planet. The New Horizons mission revealed a complex world with mountains of water ice, plains of nitrogen ice, a layered atmosphere, and possible subsurface ocean. Asterisk other dwarf planets. Haumea is notable for its elongated shape and ring system. Makemake is bright and reddish. Eris is slightly more massive than Pluto and was the catalyst for the redefinition of planet. Asterisk comets. Short-period comets originate in the Kuiper belt, their orbits occasionally perturbed by Neptune's gravity, sending them into the inner solar system. The Oort cloud. The Oort cloud is a hypothetical, spherical shell of icy bodies extending from about 2,000 to 100,000 astronomical units from the Sun over, a light-year away. It is the source of long-period comets, which can have orbits lasting thousands or millions of years. The Oort cloud is thought to contain trillions of comets, remnants of the solar system's formation scattered by the migration of the giant planets. Part 11. The future of the solar system evolution and destiny. The solar system is not static. It is a dynamic, evolving system with a future shaped by the life cycle of the Sun and the ongoing interactions of its constituent bodies. The Sun's evolution. In about 5 billion years, the Sun will exhaust its core hydrogen and leave the main sequence. It will expand into a red giant, engulfing Mercury and Venus and possibly Earth. The outer layers will be shed as a planetary nebula, leaving behind a dense white dwarf, a stellar ember that will slowly cool over trillions of years. Planetary fates. Asterisk inner planets. Mercury and Venus will be vaporized. Earth's fate is uncertain, but it may be swallowed or scorched. Asterisk outer planets. The gas and ice giants will survive, but their atmospheres and moons may be altered by the changing solar environment. Asterisk asteroids and comets. Some will be ejected from the solar system. Others may collide with planets or the Sun. Long-term evolution. Over immense timescales, gravitational interactions with passing stars and galactic tides will gradually erode the solar system. Some planets and smaller bodies may be ejected into interstellar space, while others spiral into the Sun or collide with each other. The solar system as a laboratory and legacy. The solar system is not only our home, but also a natural laboratory for understanding planetary formation, evolution, and the potential for life elsewhere. Every asteroid, comet, and moon is a time capsule, preserving clues to our origins. The exploration of the solar system by telescopes, spacecraft, and one day, humans continues to expand our knowledge and inspire our imagination. Our place in the cosmos. The journey from a cold, dark molecular cloud to a vibrant system of planets, moons, and life is a story of cosmic alchemy, chance, and relentless change. The solar system is a microcosm of the universe, a testament to the power of natural processes and the interconnectedness of all things. As we explore and understand our cosmic neighborhood, we gain not only scientific knowledge but also a deeper appreciation of our place in the grand tapestry of existence.